Yo, what's up? Welcome back. Today we are working on our custom re-implementation of zlib in Zig. Reasoning is essentially there's a lot of things that are compressed. I don't have a good enough feel for lossless compression, so let's just implement it. By implementing it, we figure out how it works. Later, we'll be able to make better decisions on like what's good compressible data, how like where like the speed trade-offs are, etc. Right? It's like mostly like a learning exercise. And since we're in a learning exercise, I've been wanting to learn Zig for a while, and so we're kind of in this like, well, this is a small scoped project that shouldn't be too long, kind of like a good dip our toes in the water for Zig, see how we feel. And so background / where we're at so far. The idea for zlib is there's this like common algorithm called like deflate. And this is like stuck inside zlib. So you have like, this is zlib, and inside him he's got like a small header where he's got like a little bit of metadata about the file that's been compressed, but then mostly he's just handing off all the heavy lifting to this like deflate algorithm. And this deflate algorithm is effectively this like list of blocks. So he's gonna like kind of chunk up the data into like some amount of pieces, and each of these pieces will be one of three types. One is like, hey, we are just exactly what we put in. Here is like the length of the thing that you fed in, and just copy paste it out. And then there's static Huffman compressed blocks and dynamic Huffman compressed blocks, where Huffman compression is you have like this list of things that you might say, right? So in English, we might use letters, right? And we can say like say we have like the string A, B, B, A, C, D or something, right? In this string, the most common letter is going to be A, second most is B, and then C and D. And so we want to like find some way to represent this where the letter A takes up the least amount of characters, and the letter B takes up the next least, and then C and D take up the least amount of characters. And so what they do is, I think it's like this. So you build like this tree where basically the farther down the tree you go, the less frequent the letters are. And then you can represent the path in this tree by saying, well, this is a binary 0, this is a binary 1, this is a binary 0, 1, 0, 1. And so you end up with this like code book where you say like, well, A is 0, B is 1, 0, C is 1, 1, 0, and D is 1, 1, 1, according to this tree. And so what ends up happening here is that if you like pack these zeros and ones into like a bit stream, then A is the A can be represented in a single bit instead of like 8 bits in a byte. So these like two blocks, Huffman blocks, they are either using a pre-agreed upon tree that is like defined in the RFC, or a dynamic one. So they like stick the specific tree for this text in this block at the beginning of the block. So where we're at right now is we've like decoded a block that has this like copy paste your shit version. We have generated the like a Huffman tree like this by hand, or not by hand. We've like made an API that allows us to generate one of these trees and decode text using the tree that we generated. But we haven't implemented anything about like actually using this in conjunction with like parsing zlib. So I think that's the plan for today, is we want to see, can we actually decompress one of these other blocks? Yeah. So plan of action is approximately these blocks in the RFC, they have like letters in them from 0 to 255, but also they might be containing references from, so if they have something in like the range of 257 to 285, then they're not just text, they're like back references. So if you have like the string like ASDF and then a bunch of shit and then ASDF, here they might say, instead of encoding this ASDF, could you just like look at the thing that you said back here? So that means that we need more than 8 bits per byte, or sorry, 8 bits in our codebook, which we don't support right now. We only support generating things that are generating a Huffman tree for ASCII or a U8 buffer. So we kind of have to fix that a little bit. So that's part one. Part two is that we need to generate a test case, right? So we have to create some sort of block that's using, some sort of compression and then try to decode that. That's part three. Part two is we want to figure out how to construct a Huffman tree from this like pre-agreed upon thing. So in the RFC, they say, hey, here is the tree you should be using. And here are like the codes. But we don't have any way to like go from this to a tree. Right now we can only generate a tree by analyzing frequencies and some text, so we have to kind of fix that a little bit. Then create a test case with fixed Huffman codes, and then we try to decompress. So not sure how far we'll get, but that's kind of like the steps. If we get through all of this, it's a good day. And if we get through half of this, it's also probably still a good day. Maybe how good of a day it is unrelated to our performance. That would be kind of cool, huh? Okay, cool. So let's get into it. So Huffman. So what's going on in here? It's been a sec since we've looked at this, like a couple streams. So when we generate this thing, we pass in a string and we count character frequencies for that string. And then we use those frequencies to kind of build up our Huffman tree from scratch. And I guess that this is just not what we want to do in this other case. Let's see. This is like a Huffman table. So this is our representation of this guy. But the output from this is actually something that we're calling a code book. So once we build up this tree, all we actually need is like a list like this. And so the question is should we go just directly to the code book? When we load? Maybe. But that's not what we're doing right now. I forgot. We're adding support for over 8-bit values. So let's start there. We'll just start by saying that our inputs for this thing may not be an array of U8s, but maybe an array of anything. So I guess this guy has to say that he's got an array of any type. Is that how this works? Created type, expected type expression found any type. Any type might be a magic word that can only go here. Okay. So maybe we'll start at like the lowest level and work our way up. So count character frequencies. He allows for us to, basically, he returns something that is a fixed array of how often we saw each character. So I guess here, this has to be a compile time parameter, which means that we have to create, this is like a no longer fixed type. This is going to be something like a function char frequencies that takes in a length parameter, I guess, and returns a type. And that type is going to be based off of the length. So this has to be compile time resolvable. And I guess there's two ways we could go about this. One is we could start going down the like generic programming rabbit hole and try to make these based off of like all compile time resolvable, everything runs on the stack. Or we could just say, fuck it, we'll use a dynamic thing. Okay. So count character frequencies in this string. Let's start here for now and see what happens. So I think here, we don't know what the type is. Any type doesn't compile here. So we need to use some sort of generic T. And two-step is suggesting a comp time T parameter, which is a type, which I think makes sense. I think I've seen, this is like the pattern I've seen in in the like, what do we want to call this? In the Zig standard library, where they like take in the type parameters their first thing, then they just take in the rest. And so then here we can do like size of t to determine how many outputs we could get here. And then I think the rest of this just makes sense, where we can zero out our whole array for all of our counts. Then we just look at each item and we try to index with that item in plus equals 1. So there's kind of like a constraint here where we need to be able to index an array by t. So bit size of is the thing too. Oh yeah, that's a really good point. This is going to give us like 1 for a U8, and we actually want 256. That's a really good point. So I don't know if we need to like, do we need to like put an assertion in here that this is a numeric type? I wonder if there's like something in the Zig standard library that we can reference. Zig standard library. Be interesting, because it seems like, well, I guess we could just try calling this with something fucked right now. Okay, so first let's fix usage of this guy. So this guy's going to use, he's going to say we're going to use U8s for now to keep the same code. Expected type this, found that. So here we throw a little const on here. And 147, this guy needs to use bit size of t. Like this. And everything else is running, so I think we're chilling. Zig build run, make sure everything looks like sane. It's not, because it's zig build and run with some input data. Index is out of bounds. Okay, so we are fucking up somewhere. Index 104, length 8. Oh, this is 2 to the power of this. So 1 shifted left by this minus 1. So here we should do like function num elms for type, and we take in a type, and we return a usize, and this is just going to be this thing. Return this. Wait, is this right? No, there's no -1 here. No -1. Because 256 elements has max element 255. So if I'm trying to get like the maximum index, I would subtract 1, but if I'm trying to get the number of elements, I don't. Num elements for type t. Okay. Let's try that. All right, so we're chilling there, and I guess we could do a little, just a quick little test-rooney. Quick one. That's just like a test num elms for type, just to make sure that we're not doing anything fucking stupid. So if we say num elms for type U8, we should say stud testing expect equal num elements for type 8, and this should be 256. And if we say U16, we should see 16384. And I should actually be running zig build test here. He doesn't like this because I need to write try on these. 16384 might not be right. 2 to the power of 16. 65536, of course. Oopsies. I love how almost every Twitch streamer uses Vim, VI, and Vim. Well, it's just like nice, you know? It's just nice. Okay. Looks like we're chilling. There's an error here, but that's just because one of my tests triggers an error case. But that's okay. Like, we're still exit code zeroing here, so we're fine. Okay. What's next? So our code book, our character frequencies now can be any type, and so we just have to kind of extend that. Okay. So this is used here. So now we can want to say, hey, this guy, our Huffman table, let's see, what does he hold in him? He holds this node array, which has a list of nodes. The nodes have just leaves and branches. So in reality, he doesn't really hold anything related to the size of the type. And I guess probably just when we generate the codebook, we just assume that it's 4 U8s. That's interesting. Interesting. Node from code. So this is the path that we use to get to the node. So that's again the output. So we have also this code should not necessarily be a U8 either. Okay. So what does he actually do with these frequencies? He says, hey, for each frequency, so this is 256 right now, we append to the node list if with the count. Okay. And then we just pop. So there's actually nothing related to number of elements here at all. Which means that this guy could just take in an array of any t. Does it make more sense for me to type any type here and then assert that it's a slice? How do you do that? I've seen it somewhere in the standard library. Maybe we can just go into... Do I have Zig cloned here? No, but we can just clone it. And take a little peek skis. Is this gonna... I should have done shallow clone. But it is kind of nice to have the whole history. I prefer it if it's not that bad. This looks like it's going to be, what? 250 megs? That's not the end of the world. We can tank that. Just give him a sec. And while that's happening, we can search the standard library documentation ourselves. So I think it's stood mem, probably. I've seen something that's slice. If you assert the slice, you lose some coercions, like array pointer. Oh, interesting. Because it seems silly to force the user to type the type if I don't need them to. But it does seem like this is the standard library way. I just don't really like it. I don't like it. Let's just see. We'll search for an example. So we can go to lib stood, and we can just kind of grep for compile error slice. Ah, yeah. Type contains slice. Oh. This isn't really what I want. Compile error slice. Expected pointer, slice array, or vector type. Oh, this looks very... So this is pub function elem. He gives me back the type of the element side. Yeah, I'm not really sure if this is what I want. But we could look in std meta to see if there's something like that. Std meta. So this is like meta programming helpers. So is there like a, hey, I want to make sure that this is an array. Container layout. No. All right. What is this? Pub functions A. What is this? Why does this exist? Oh, it just because it's in tests. That's pretty funny. So those got like exported somehow by mistake. That's really funny. Okay. Yeah, fuck it. We'll just do it this way. It's fine. So lm type or const t. No, comp time t is a type, and then here we have const t as our input, and then here we pass in t here. What the fuck is foo doing in there? Autodoc got a complete overhaul, so yeah, I think it's probably that these guys are showing up in tests, right? And they're probably just doing something like searching for public functions and putting them in the autodoc. Okay, so now surely there were users of this that are just fucked now. So here we'll write U8 here. And who else uses this guy in main? Okay. Easy. And then the code book here needs to generate based off of the number of elements here. Which means that this guy also has to get the same treatment as whoever else we were looking at before. Where'd he go? The character frequency count. And I'm kind of thinking now, what if somebody wants to like generate Huffman codes for like U32s? Like this is going to get bigger and bigger to the point where just having an array of values doesn't necessarily make sense, right? But I think that maybe we just don't support that for now. We just tell them to fuck themselves. Yeah, it's fine. It's fine. And Zig has types that are for like, you know, if I wanted to say U12, Zig supports that, so that's probably fine as well. Okay, sure. So here let's take num elements for type and slap it. Actually, there's fine. I think that you don't need to declare functions before you use them in this language. So this is, again, we're going to say pub function codebook, and he's going to take in a type and return a array of num elements for type t code like this. No, he returns a type. My bad. And then the type is this. Okay. And then wherever we use codebook, we have to replace this with t. And I guess, like, technically this type has to be consistent. Like, the codebook we're generating has to be consistent with the data that we fed in. So it's almost like we need to store that information in here. So like data type is a T. And how does this work? Do we make, I guess if we're storing it, can we store something just like as a runtime type? Does it need to be a runtime type? I guess not. I guess it should be a compile time type, which makes this guy turn into a function. So this guy takes in a type, and he returns a type. That is this, and then we return this struct. Return struct this, blah, blah, blah. So now type doesn't end up in init, he ends up over here. And we say const data type is equal to t here. Oh, we don't even need to actually store that anywhere because we just can use t everywhere now. So here we're generating a codebook of codebook t, like this. That sounds kind of right. So, okay, this is there's all sorts of things that are gonna be broken here, and I guess we just start going one by one and fix them. So, our Huffman table init is wrong now, so this is in main zig, Huffman table init here. This is, now we're gonna say Huffman table u8 init like this. Okay, that's one. Huffman zig 39, we have, what is he complaining about? Expected type found function type. Oh, because now we need to use const self is equal to this, and then here we refer to the Huffman table itself. Okay. Here we have to go back to main zig and look for Huffman table. Everywhere we use these, we need to write u8 now. Okay. Now we're at some codebook problems. So we changed our codebook to be type dependent as well. So now we just write u8s here as well, I guess. Huffman zig 106. So this is now const self, because that's a generic type, or a function that generates a type, I should say. Same here, and here, and here. Okay. 224. Huffman writer, he needs to take in a codebook. We'll call it a codebook of u8s for now. And we'll fix it later. I wish that I got more than one compiler at a time. That'd be so cool. So cool. Okay, so the reader takes in a Huffman table of, I guess we'll just hard code this as u8 for now and come back for it. I just want to like get compiling, you know? And 199, he also needs u8s in our writer. 234. Okay. So zig build and this, and our normal thing still works, which is great. Superb. And now we can start looking for places where we hard-coded u8 and try to clean them up a little bit. So I guess we can look for bracket u8 bracket and just try to figure out. So our Huffman writers, here we take in some sort of codebook. And we use that codebook as a lookup. Right, so we say, hey, we have some data of some given type, and we're going to look up that thing. But I guess on our writer side, we're actually working on reading right now. So the writer can stay as is. We don't really care about the writer right now. But our reader, he is going to say, well, this thing might not be a u8. So I guess what we're going to do is we're going to say, hey, what's our output type? Yeah. And so now this Huffman table U8 is going to be output. And yeah, okay. Chilling there. Huffman reader now is going to take in a table. And I guess here we say table isn't any type. And then we create a new Huffman reader with the type of table. And then we just assign table here. Sounds right? Sounds right? Hello. Hello, hello. Welcome, welcome. Huffman.zig 283. Looking sharp. Oh yeah, my head looks different. At my at a job I used to work at, when people got haircuts, we would point at them and laugh and say, "Ha, your head looks different than it did yesterday." It was a good little game we played. It was just so fucking stupid. What's it complaining about? Expected type this, found type that. Huffman table 283. Did I just fuck up the table argument here? Const Huffman table output. So I'm expecting. Oh, I'm an idiot. I'm an idiot. So this table, the Huffman table has a data type inside, and that's what we're supposed to be copying here. So this is const data type is equal to t. Is this how I do this? And then here I extract the table type. No, this seems fucking stupid. But I guess, yeah, we do need to know. We do need to know. So we say table dot data type. And you think data type needs to be public, but maybe only if it's used from a different module. I guess we'll find out. No field name data type. Did I not? Huffman table data type. Oh, I need to do, oh god damn it, type of table dot data. Gross. That's disgusting. Oh, but now this is a pointer. Oh, so I have to like dereference it. Oopsies, but it's dereferencing in this language is like this. Okay, so that compiles, but like, this is awful, right? So what happens here is table is supposed to be a pointer to a Huffman table with like a, that's like generated based off of like U13s or something, right? The reason that we do this is because inside the table, we have to count frequencies, or I guess we have like table generate codebook, which has to return a something. Codebook associated with U13s. So we store the type inside, but then like now this guy needs to know that type. So then we store the type inside, dereference this pointer, grab the type of the pointer, and look at its associated data type. Like, something about this just feels fucking wrong. Can I do this? No? Like, something about this just feels fucky-wucky, you know? I wonder if I could do something like, there's also stood meta child pointer. What the fuck is that? What the fuck is that? Meta child. Given a parameter's type, returns the child type. Array, vector, pointer, optional. So treating an array and a pointer here is the same? I don't like that. And then, like, how am I supposed to, like, I wish the types here would document that I want this table to be a pointer, right? Like, why can't I do star any type here? You know? You know, zig pointer to any type. Yeah, that's not going to give me anything of value, huh? Blech. Like, zig people in chat, like, is this... This feels like fucking insane to me. But is this just like normal zig? Like specific, like it just looks like, what the fuck? What the fuck? But I guess we'll just keep going for now, and we'll just put like a fix me. Maybe try finding a way around this type ridiculousness. All right. Is there something else we should be doing here? Maybe. Okay, let's break this down a little bit more. So there's two type lengths, right? There's one which is, or like there's two sizes. One is like how far down this tree you're willing to go, right? Like the depth of the tree. This is one size here. Why is it insane for the clues in chat? It's just not like pretty. It's like it feels like I'm writing too much. It feels like I'm packing too much complexity into one statement with like no way around it. I can't reduce this complexity by factoring it out. At least maybe I can't. Maybe I can. It feels like I can't. So it just feels nasty. But let me think about this a little more. So on the reader side, so say we have some tree like this. Now, what it is outputting happens to be these like U8s right now. If we fill this up with B, A, C, right? But like, there's no reason that this tree is almost independent of what it's generating, right? We are kind of deciding when we use this that the thing we care about is, you know, maybe this is like a 2-byte array. So if we treated it that way, then we would say, okay, when we generate this thing based off of our character frequencies, we kind of need to know, we could argue that the user of this table should keep track of what it's representing. Okay, so what is the value? I missed an important piece here. Right here. This leaf node type is very important. Because here, somewhere in the tree, it needs to store this. So it is important. Fuck, we do need to keep this in. Okay. We need to give the same treatment to node. Pug function node. He takes in a comp time type, and he returns another type. And so this becomes return, and we indent everything, and we put a new thing here, and leaf is a T. Here we go. This is the important part that I was missing. This makes it all start to make sense again. So now our node array is a node T. Yes. Comp time, oopsies, this is comp time T is a type, not time type is a T. Okay. So then data type doesn't necessarily make sense. Can you do like a function here? If I was like pub function data type. Oh, I guess I don't need to do that. It's just const data type CLT. Yeah, okay, that's fine. That's fine. Okay. Does that all kind of line up? Node from code. Node from code. What the fuck is a comp time T? Why not just T? Because I think that we have to say that we are making a function that generates a type, and the input to that function needs to be resolvable at compile time. I think. Comp time, I think, is saying for this parameter, this has to be resolvable. This is not like a runtime thing. And you can, it doesn't have to be types that you can do that with too, right? You write a function, it's like pub function, like do math, and you could take in like a compile time I32 and return a new I32, I think. And then you could do like return v times 2. And then I think that if you call this function, this will like resolve at compile time. It won't like do this math at runtime. It'll do it and like hard code v times 2 into the output binary, I think. Not really sure. But that's my understanding so far. And so you're saying, well, shouldn't like comp time t, like what, there's no such thing as runtime t? And I think it's probably just for like compiler consistency. That's my guess. That's my guess. All right, yeah, I guess we'll just leave this. I would like a way to, like, in my API, specify that I expect a pointer here. But I guess that that's just not the Zig way. I guess I can at least do a, like, if type switch type info of type of table or something. At the very least, I can do pointer is good, and anything else, we can say compile error expected pointer to Huffman table as table parameter. And we can probably even go a little farther where we can like extract the value here. And we can say like v child is equal to Huffman table. Something like this. Huffman table. I guess I can't check that it is exactly a Huffman table. Let's just try passing in an invalid type here and see, maybe the compiler will like already give us a reasonable argument here. So if we say Huffman reader here, and I just put in like data, like a U8 array, like how fucked does this get? He's just gonna get mad that I can't call this. Ugh. Oh, that's awful. Okay. I would like to see like a nice compile error here as well, being like table needs to be this parameter, but find way to error gracefully on invalid table input. But for now, we'll just take it as is. Okay. So our table stores nodes based off of count for character frequencies. Probably should work now, so we can do a little how do we want to test this now? We could go into main and we could try constructing a Huffman table out of something else. So var table is equal to Huffman table based around U4s. Table, and we need to initialize this with initialize this with an allocator, I guess, as well as an array of some U4s. So 1, 2, 3, 4, 4, 3, 3, 1 or something. I don't know. And we can say var code book is equal to table generate codebook. I don't know why that's not working, but that's okay. And then std debug print any code book. So hopefully at this point, it fucking doesn't compile because we didn't put a little ampersand here. No field are called generate codebook. So is it because I still have to write try here or something? Expected 2 arguments. Oh, nice. Okay. So we can say var codebook is equal to huffman codebook u4 is undefined, and then we can pass in the codebook here. And then, is this a failable thing? It is. Expected 2 arguments, found 1. Really? Oh, allocator, of course. Zig, build, and run. So we do get a codebook that has 0 nulled out, 1, 2, 3, 4, and then everything else nulled out. And then everything here is taking 2 bits, which is kind of interesting. Can we kind of bias this towards 1s and 3s or something? So 1s, 2 bits, 2, 3 bits, 3, 1 bit, 4, 3 bits. Yeah, okay. Cool. Cool. Yeah, I think we're good. So all of that was to add support for greater than 8-bit. I guess we should try also with instead of U4, U6, U10 or something. And that did just make a way bigger array, but we still only see 1, 2, 3, 4 filled in. Looks like it's working. He is complaining about things not being deallocated, which is pretty reasonable. So defer table d init is probably what it's looking for. Yeah, okay. Nothing to worry about. Okay. So we have a Huffman table that now supports anything. Can we construct him from these length codes? So let's see. These are using this thing called like canonical Huffman encoding. And the idea is that like you can build your tree. You kind of build up your tree based off character frequencies, right? So you have like A, B, 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 C, D or something, right? And the way that like the building works is you just say like, hey, let me find like the 2 least frequent things in here. So here, if we were to like put out the character frequencies, it would be like 5 A's, 3 B's, 1 C, 1 D. And you can look at this and you go like, okay, give me like the smallest things from here. So my smallest things are going to be C and D. So I like construct a little node, C, D, and then I like put this back in. So now I have like 5 A's, 3 B's, and then this like character count of 2 that is like both of these combined. And you just kind of build this up, and so then you say like, okay, I'm gonna make a new branch that has like B and C, D. But the order that you have, there's actually like a bunch of valid trees for this same combination. You could have like B and DC like this. And this would be equally valid, but these would create like different Huffman codes, right? So this would be 0, 0 for D, 0, 1 for C, and 1 for B, versus 0 for B, 1, 0 for C, 1, 1 for D. And so the canonical Huffman encoding is they basically assign what order these things should be in. So we need to figure out how that works. And I think that like what they say is basically with this canonical encoding, the only thing you need to reconstruct the tree is the number of bits for each element. And so I guess we have to figure out how the fuck does that work? How does that work? So the number of bits for each symbol can be transmitted as this. And so I guess we just need to figure out how, we need to read about how do we build up the tree from this. Given a list of symbols sorted by bit length, the following pseudocode will print a canonical Huffman codebook. Oh, here we go. Perfect. So the code is this, which is while more symbols. Whoa, what the fuck? Code is equal to 0. While there are more symbols, we print symbol encode. Okay, so that's not pseudocode for an algorithm, but okay. We will print out the symbol encode. And so the code is equal to code plus 1 shifted left by the bit length of the next symbol minus the current bit length. What? What the fuck are they talking about? Okay, so this print is like replacing, like you could replace this print with whatever. So here they're saying, say you have codes for A, B, C, and D. You would start with A would be 0. No, that doesn't make sense. But it does kind of seem that way, huh? Where they're printing a code equal to 0 right off rip. Tell me what this doesn't make sense. Let's look at our original Huffman codebook. A is 1, 1, B is 0, C is 1, 1, D is 0, 0, 0. Okay, so here they have B is the most frequent thing, A is the most frequent, or second most frequent, C and D share. There are several ways to encode the Huffman tree. Yep. Since we're listing the symbols in sequential alphabetical order, we can omit the symbols themselves. Okay, so, right, so here's he's saying, hey, this is character A, he takes 2 bits and they're 11. With our canonical version, we have knowledge that the symbols are in sequential alphabetical order, and that a later code always will be higher in value than an earlier one. Symbols are sequential alphabetical. Yes, okay, sequential alphabetical order. What is this magic? I guess sorted by length is an important point. Yeah, it must be. There must be something about like the input to the algorithm that I'm missing. The only parts left to transmit bit length for each symbol. Okay, so we have A, 10, code value 2, bits 2, 2, 1, 3, 3. With this knowledge, the canonical Huffman algorithm is then possible to recreate the entire symbol from just the bit lengths. Unused symbols are normally transmitted as having 0 bit length. Okay, another efficient way of representing the codebook is to list all symbols in increasing order by their bit lengths and record the number of symbols for each bit length. Okay, here, blah, blah, blah. But we don't need to do that because, okay, so given a list of symbols sorted by bit length. I see. Sorted by bit length and by value. That's probably the important piece here. So if you were to say, yes, okay. I think I'm seeing it. So if we took our codebook for this ABCD. Let's say that our A is A would be 1 bit, B would be 2 bits, C would be 3, and D would be 3. Okay. Then we encode that as 1, 2, 3, 3. Then when we decode this, we have to pair these back together with their letters. So in our in-memory representation, we'd have like 1A, 2B, and then 3C, 3D. And then we could just sort these tuples by first their number, then their letter. And then we can run this algorithm. And I think that makes sense. Where here, I think they fucked up the order of printing here as well. I think that the printing here, the code has to be assigned before they print. Okay. I think that makes sense. So my only the only thing I want to double check is how are these guys supposed to be stored in the tree themselves? So it looks like left on the tree is supposed to be the leaf node, and then right is further branches. All right, yeah, simple. Okay. Oh, okay, wait, no, so this actually does make sense. This code starting at 0 means that even if your bit length is like 7, you're going to take 7 lefts to get there. And so it's 0, 0, 0, 0, 0, 0, 0, 0. Okay, no, okay, I think that makes sense. That makes sense. So when we read, we are reading based off of our Huffman table representation. And so maybe we make some function init from bit lengths. Yes. And he needs to take in an allocator. And he's going to return a self. Const allocator is equal to mem allocator. Okay. Okay. Then we need our bit lengths. And so this is going to be, it's going to be an array of, we'll say U8s, right? If our Huffman tree depth is bigger than 256, it could be. U16, U64, fuck it, doesn't matter. And then we have num elms for type t, number of bit lengths. Okay. So let's just start by making this unreachable so that this will compile, and then we can start like logging stuff based off this. So what do we want to do first? First, we want to pair each item with its bit length, which is already done, right? Kind of, it's paired by its index in the array. Yes. Okay. So what? We start by saying code for oh, right. Okay. So we have to create a array list var lm struct. We need a struct. We'll start here. Const lm and with bit length. Okay. lm is a t, bit length is a U64. Simple. Now, with this, we can say we're going to make a list of these guys. So this is going to be the same thing. We're going to say var counts is equal to lm lengths is going to be bit lengths. We're going to copy each one in. So here we're going to say this is going to be a num elms for type t, but now we're going to call it elm with bit length is equal to undefined, and we're going to for bit length, we're going to extract each individual bit length, and we're going to say that lm lengths at that value is equal to a struct with the lm of I. Yes, here we go. bit length is equal to bit length. Yes. And then we just need to sort this thing. Surely there's like stud sort. Can we like sort an array automatically in here? Zig standard library. Surely there is a way to sort a slice. Here we go. How is this guy implemented? Function sort. Stood sort block. In stable in place sort. ON best case, ON login worst case. Okay, sure. Seems reasonable. Stood sort. So this is called block. Weird name, but okay. So we want to pass in the type that we're sorting, which is elem with bit length. Items is elem lengths. Context is any type. So here, I guess we're just going to write nothing. Our context doesn't fucking matter. And our less than function is going to be, I guess, elem with bit length less than. Sure. And that means that we should define a less than function who takes in a type of context. Is there like a void? I guess that's just void. Yeah, I guess. So we say context void LHS lm with bit length RHS lm with bit length. And he returns a bool. And all he has to do is say LHS if LHS dot bit length is less than RHS bit length. I guess if RHS bit length is less than or equal to, return less than, return true. Yeah. Otherwise, it's a tie. Or else if no, it's if LHS bit length is equal to RHS bit length. There we go. Then we need to do the tiebreaker. So we return LHS.lm is less than RHS.lm. And otherwise, then we can just return LHS bit length is like less than RHS bit length. So this should sort by bit lengths first, then element second, which is exactly what we want, I think. This needs to be probably self or something. Not self is equal to this. Ambiguous reference? Oh, because there's like external types maybe. Unused function parameter. This equals context. And you're saying maybe I should write context any type? I was thinking that. I guess like, but like void seems fine too. Pointless discard a function parameter here. Okay. It looks like that works, but probably this wasn't compiled actually, so we need to var table 2 is equal to huffman table u3 u2. Yeah. Init from bit lengths. And then we can pass in our allocator and then we want to pass in 4 bit lengths. So we're just going to say like 3, 3, 2, and 1. I think that makes sense. Table 2. Any, and we can then print out table 2. And then surely this will break in some way. Yeah, so here, expected 464 found pointer to 464, so I'm supposed to delete that ampersand. Expected U2 found U size? Okay, so what's going on there? I guess this has to be incast, which is fair. There's no like compile time guarantee that those match up. Array literal requires address of pointer. So that's here. Expected function type of this, blah, blah, blah. Void cannot be cast into, okay. So can I say that my context is just, I guess I can't. I just have to say any type here, like you suggested. Which is annoying. It is what it is. Generic function cannot cast into a non-generic function. Can I like, how do I make like void context zig? I'm sure I've seen this somewhere. Like reader. I think I've seen a context void in here somewhere. What will we need to work? Just need to pass literal. It's because I used the dot, not the, wherever I called this thing, I used dot squiggly braces instead of just the squiggly braces. That's what you're saying. Nice. Okay. Expected type found function comp time type. Whoa. So this is in line 23. Okay, so we can't format nodes anymore because they're generic. Okay. So we did manage to get to the unreachable part now. So this all compiles now, and it would be interesting maybe to print these things. So let's do that. So we'll print out our LM lengths. Okay. Yeah, so we have 3 first, then 2, then 0, then 1. Yeah, okay, that looks right. This is sorted in the right direction at least. Okay, so now I think that we ignore anything that has a length of 0. So now we iterate over these things. We say for LM lengths. We're going to have an LM length for each one of these. And if LM length bit length is equal to 0, we continue. There's nothing to do. Then we have to, where is the thing here? We now know the code associated with this symbol. So let's just do what they said. Print code is code. And LM is LM. So LM, I guess we probably want something like just like this. So LM length dot LM goes to LM length or code. And I guess maybe we want code first. No, it's fine. Code on the right's fine. Okay. And then we need to do this thing. So code is equal to code bit plus 1 shifted left by bit length of the next symbol. minus current bit length. So this is lm length bit length. And, oh, this is ugly. I don't like this. Does this make sense? So they're saying like, hey, we increment the code by 1. So if the bit length has increased from the last bit length, we're shifting left by 1. Otherwise, we're not, right? That's all they're saying. So we can actually just store last bit length is equal to 0. Then if last bit length is greater than lm length bit length, we like shift left by 1. But only after we plus 1. Last bit length is equal to lm length bit length. And then code equal to code plus 1 unconditionally. Okay. Sure. I guess this isn't quite true. I guess we should just do what they did. I think that what I wrote is slightly wrong. So can we just, instead of doing this for loop, we'll do for 0 to lm lengths len. We'll extract I here. And if I is equal to lm lengths len minus 1, then we don't do this, but in all other cases, we do. Okay. Print here. No. If this is, so L bit length of the next symbol, this is lm lengths I plus 1 bit length minus lm length bit length. Const lm length is equal to lm lengths I. Okay. And here we just say var next bit length is equal to, if we're at the end, then we just say it's the same. Like this, else. Do I need to do like a block and break? It's something like break block with this. And then here we would like assign the label block or something. Just remove the curlies. Zig return from if. Like, I know that's not if expression documentation. Somewhere they're going to talk about ifs in here. Values, operators, vectors, pointers. You're saying that I just do it without curly. I see, just like without curlies, completely. But that's surprising to me. But it does look like that's what they do here. But what if it was like a more complex thing? I guess it's fine. Okay. So it's this, else it is lm lengths I plus 1 bit length. Okay. And then here I can say next bit length minus. Hello, why can't I delete till minus? That's very strange. I've never. Oh, probably because that minus was copy pasted out of some other fucking character. Annoying. All right, let's just see if that does something, Zane. Var code is equal to 0. So this probably has to be like a U64 or something. Expected type U6 found U64, so we have to int cast this to make sure that it is a fair shift. Okay. So here, we want to print these codes as binary, I guess. Actually, no, we don't want to print those. We'll just print them like, we don't want the leading 0B. That looks ugly. Okay. So given our thing, we have 3 is code 0, 2 is 1, 0, 0 is 1, 1, 0, and 1 is 1, 1, 1. I think that's right. Right, we have things that are increasing in value are increasing in value. And now what we have to do is we actually have to generate the tree from this, which is a little bit trickier. So probably what that looks like is we have to create a tree and basically walk each of these paths and insert branches into our tree as we go. Which is not really like, probably there's some sort of more efficient representation of this guy, but that's okay. So I think what we're gonna do is we're basically gonna have like a tree that's empty, and we're gonna see the code like 3 is 0. And we're gonna go, okay, we're gonna walk 0, which means that this guy needs to have a left and a right. So we're gonna make this guy a branch node. Then we're going to make a leaf node here that says 3, and then we're going to see the next guy, and 2 is going to be 1, 0. So we're going to be like, okay, this right branch needs to point to somewhere, so we'll fill that in, and then we'll create a new node here, and then go left and right off that, which is kind of a pain in the ass, but also maybe fine. Okay. Okay. So, nodes is going to be a std array list of nodes. And what's kind of fucked is there's an assumption about like the order of our nodes at this point. Because like the way that we built the tree originally was based off of character frequencies. So by doing it this way, it would be nice to hold that assumption. Is that possible? We could start at the bottom. Yeah, I think the way we built it before is we started with only leaf nodes. And then we built up branch nodes as we walked up the tree as we went. Is that something we can do here? Like, does that workflow still make sense? So we have like 1, 1, 1, 0, and 2, or 0, 1, 1, 1, 1. And so say we like shove all of these nodes in there. Boom, boom. Then our branch nodes, can we construct them in like reverse order? I guess. We know that like these guys are paired together. We know that this is going to be like 0, 1. Yeah, maybe. Maybe. I guess let's just try it and see what happens. So for for 0-bit lengths len, we have bit length. If bit length is equal to 0, we continue. We don't need leaf nodes for anything that aren't in the tree. Otherwise, we create a leaf node. So nodes append a leaf node whose value is unknown. Fuck. We'll do this. Oh no, its value is just this is I, sorry. And then bit lengths I is this, and then leaf is I. Yeah. Just make sure that compiles. It does not because it's a pointless discard of alloc. We need to specify that our node is of type T, and our leaf we need to put this inside another thing. So we use squiggle braces to turn this into the union that it's supposed to be. Expected type found type of enum literal. Did I fuck up? Nodes is a node array. Array list node T. So maybe we'll just use node array here instead. Even though it's the same shit. I don't think that's changed anything. And then I must have just fucked up. Nodes append. Oh yeah, I used this dot leaf equals. Ah. It's like this. Equals in cast I. Okay. So now we have a bunch of leaf nodes, and then we just have to set up the branches. Which means we're probably iterating over. Ugh, what a pain. What a pain. So probably if we iterate over our elem lengths in like reverse order. Something like this. While I is greater than 0, I minus equals 1. So this will iterate in reverse order. We can insert branches for pairs of these guys. Let's think about this. So if I have A, B, C, D, E, I have to like pairing up D and E will make a lot of sense. But then it's like, do I pair up B and C or C and the combo of D, E? So maybe this just doesn't work. Maybe it makes more sense to just lazily instantiate branches. That probably makes more sense. And then we just have to fix this assumption. But I think this is the only assumption that matters, where like it assumes that the root is the last thing we inserted, and we can just store the root. Sure, I guess it's kind of annoying, but it'll have to do. It'll have to do. I'm positive too that I'm like missing some optimizations here, by the way. Like, surely this can be done more effectively, but get fucked, me, I guess, you know? Sometimes you just can't get there easily. Or sometimes it's nicer to start with something that works and then refine later. All right. All right, so we're going to say for elem lengths. No. We have codes now. And so I guess for each code we generate, let's just walk the code. Which it looks very similar to this node from code thing, where we start at the root. And okay. Here's what we'll do. We need to make our node array still. So it's node array init alloc. And the first thing we know that we're going to have a root. So we'll append a branch node. But we don't know what's in it yet. So here, how do I branch? He's got a left is equal to usize. Is there like a max? How do I get maxes for here? Usize. Seems like you use the encoding somehow decide to construct the tree. It does feel like that way, for sure. But I think I'm just going to do what makes most sense in my head right now. How do I get like the maximum value? Std math max int. Yeah, there it is. Thanks. Std math max int usize. So here we have the root of the tree. And then for each code, we're just going to say hold on. So the codes here are the oh god. It is that the most significant bit is the first part. Oh, that's fucking annoying. So we have to like determine what the largest one value is? Oh, that's fucking annoying, man. Because here, like for 2 here, we want to like walk right then left in order to resolve the tree. Or resolve like where in the tree something is. But that means we need to find the most significant bit. So MSB, I don't know, man. Let's just keep plowing and we'll get somewhere. Function MSB. Most significant bit for a given value. Which I think that we are storing as U64. This will return another, I don't know, it doesn't fucking matter, U64. We can do like for I in 0 to 64. You're saying that there might be a built-in for this? That would be nice. I don't have to write by hand. C something. Counts the number of least significant trailing in a big endian sense zeros in an integer. Not quite what I want. But count That's fine. That's fine. We'll just do it. So, we shift right by some value. Most significant set bit is what we're looking for. So we want to shift val by I. And if this is 0, return I minus 1. You're saying CLZ. Counts the number of most significant leading blah, 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 blah. Most significant zeros in integer. Count leading zeros. So, yeah. So you can just do the bit width minus this. Yeah. You're right. Nice. So we do like CLZ of code. Okay. And that's going to give us some shift. I wonder if we can get away with doing something crazy like stood IO bit reader with big endian. But that's good. That's going to require stream. What a pain in my ass. Okay, here what we'll do. Function. We're going to make an iterator. Yes. Okay, code iter. I like that. Yes, this is what I want. And then in this code iterator, we're going to have our code, which is a U64, and our bit index, which is going to be, what, like a U8 or something. It doesn't fucking matter. U for U8, U7, U6. Whatever, it doesn't matter. When we initialize this thing, it's pretty bonkers how C compilers will look at a loop like this and replace it with a single CLZ instruction. Yeah, if they can manage that to optimize my shitty code that way, that is very, very impressive. It's something that I would like to look into sometime, is like, I don't understand how these like optimizers work, but they seem very, like, it seems like it must be an interesting rabbit hole to go down at some point. Okay, so we're going to initialize with some code. And we're going to start with our bit index. We're going to return a struct, and the bit index is going to be initialized with the number of leading zeros. Yes. Dot bit index is equal to CLZ code, and the code is equal to code. And when we try to go next, we are going to return a bool of whether or not we're going left or right, or if we're done. If bit index is equal to 64, we return null. Static bit set has an iterator if that's what you're doing. God damn it. Returns the optimal static bit set for a type. So here I specify the size of the bit set, and then I could iterate over the values there. It's fine. I don't really want to learn that right now. I'm just going to do this. I'm going to keep going. We can figure it out. So I guess the bit index maybe should be decreasing so that we can use it as our shift. Whatever, it doesn't matter. So we're going to say code is going to be shifted right by 64 minus self bit index and truncated to U1. Or I guess, I don't know if the truncate's going to work here, so we're just going to say shift this right by that much and with 0x1. And if this is greater than or is not equal to 0, then it's true. Okay. And then I guess var ret is equal to this, return ret, and then before we return we say self bit index plus equals 1. So I think that now we should be able to construct this thing, and he's going to iterate from the most significant one downwards and give us whether or not we should go right or left. I think. So we can write a little test for that. Code huffman code iter. So we're going to construct this thing with like 0b 1 1 0 1. Easy. And then we're going to say while it next I guess what are we going to do here? We want to push these into an array probably. Var path is equal to stood array list of bools in it with stood testing allocator. And then here we just do path append val. And then at the end we can say stood testing expect slice equals equal slices of a bunt 4 bools should go true, true, false, true. And that should be our path. And which way do they want this? They want the expected value to come first, which is what we did. Lots of mistakes here. So no function member init in this function. So 390. So right, this is a U8 now, like this. We haven't fixed all of our tests from all of the shit we did before. 393 codebook. This should be for U8 as well. Expect equal slices. Expected 3 arguments found 2. So this should be U8. Error is ignored at 112. 423. This has to be try as well. 267. He doesn't like that this might be an invalid shift size. I need to use address of to fix this slice thing. And then I think the last one was at 132. We left this CLZ in, we shouldn't have. All right. Array literal requires address of operator. What the fuck? Oh. This is supposed to say bool here, not U8. There we go. We're so close. This needs to say path items. And this is wrong now. So we found true, true. We expected true, true, false, true. We found false, true, true, false. So it looks like an off by 1 probably on our initialization here. This guy should be +1. So now we expected true, true, false, true, but we got found true, true, false. So what we're expecting to see, just to clarify, is this like 1101 should result in true, true, false, true. We're trying to iterate over bits of this index. Could just be that we're off by 1 there. And then all we have to do is fix the leak here. So it's just defer path deinit. And there we go. That test now passed, so we can probably assume that this like code iterator is going to work correctly. And now when we want to build our tree from Huffman codes, we should be able to say var code it is equal to code iter init code. Yep. And while code it next walk direction is what we're going to call this. We're going to do something based off the walk direction. So if it's true, we're going to try to walk right. And if it's false, we're going to try to walk left. So I guess our node is going to be some sort of reference to some node in our thing. So we're going to start it at nodes items 0. Right, so this is the root as we put it in here. And if we try to walk left or walk right, we're going to say node is equal to node right, except we need to ensure that the node is a branch. So here we need to like switch node. And if it is a branch, we just return B. And else, we're just going to call this unreachable for now. Yep. And so here, maybe we'll call this node index, and we'll start at node index 0. That will make things simpler in a second. So it's like const node is equal to nodes items node idx by address. And so here, if we are walking right, we take branch out right. Otherwise, we take branch out left. Easy. Okay. So once we are done walking, we should have a leaf node. But we need to ensure that the node exists. That's important too. So, because it won't exist here, and it might not exist here. So here we need to say if node idx is equal to something is greater or equal to our node's length, we need to update the previous branch. Fuck. So this has to be done down here. Let's do this. We will write a little helper function. Ensure idx in array. In node list, we'll call it. And we have our comp time type, which is the type of element we're storing in our node list, as well as our nodes, which is a std array list of nodes of t. Okay. So what are we going to do here? We need also taken the index. Okay. So if idx is greater than or equal to nodes items len, I guess if idx is less than this, we can return, then the work path is one indent level up, which I prefer. Then we can do something like nodes. What do this is wrong. This is wrong. We're not trying to ensure IDX in the list. We're trying to add empty branch to node list. There we go. And this is going to return the index of the thing we added. So here we're just going to say no try nodes append. Essentially this. Yes. Add empty branch to node list. And this can be done here. And we have to say if branch.write is equal to stud math max in usize. We node index is equal to this. Else it's equal to the right branch. No. We say branch right is equal to this. There we go. Here it is, baby. Here it is. We do the same thing here, but for left. Yes, there it is. And so now, this node will always exist, but it will be an empty branch. We just have to reassign it as a leaf node. So node is equal to a leaf with the element inside. I think it's like this. And there's like a chance that this works. Not a really good chance, but there's a chance. Add empty branch node list. So this guy needs to have a T here. Okay. And it needs to be here as well. And then here we return nodes, items, len -1. Okay. Error is ignored, right? So try here, try here, try here. And value here is ignored, so that's fine. We know this is gonna be 0. Node IDX needs a type. I guess this should be usize. And var branch is switch node. Does it need to be dereferenced or something? Expected type found type of enum literal. So when I assign these, does it become like this or something? I can't remember. I can never fucking remember. We can just look at... I don't know how to assign unions in this language. Fuck! Oh, it's equals. Like this. Ah, there it is. Okay. Implicitly return self. Right, so we need to say nodes equals nodes. Like this. Return nodes equals nodes. Okay. And let's run it. Okay, so it did something. So it did construct a table. And he has a bunch of branches that are unresolved, which is really bad. And no leaf nodes, also really bad. So really we just fucked up all sorts of ways here. So let's see. let's see here. So first of all, why are these reassignments not happening? Probably because I need to take this by reference. So is it like this? I put an ampersand here, a star here. That looks different because I segfaulted. Panic, reach unreachable code at this 135. So that's not good. Node IDX branch right, node IDX branch left. Node is equal to node index. I guess we're gonna have to start doing some logging. Maybe for each code in here. I think you need to do add no branch since node.star creates a copy. Oh. Switch node. But like node.branch, I don't know if that's valid, right? Oh, so I can switch here to determine that this is valid. But you're kind of saying I can just do this. And I think Zig will complain at me if that's not right. No field named branch. Capital B. Okay. Yes. Panic access of union branch will leave is active. Okay, that's a good sign. And the question would be, why? Why? So I guess we can do switch node. Let's just maybe try to get out of the crash scenario. So let's just leave stood log error what the fuck leave. Else prong required when switching on type Huffman node 2. Does it, because I need to dereference it maybe? And this guy needs a little argument there. Okay, so we got WTF leaf, and I'm supposed to continue here. Okay, so that happened twice. And so now let's try to figure out what the fuck is going on there. Stood debug print node index is this thing. And maybe we should log the code as well. That code is this thing. So maybe we form it as binary. Okay. So here I forgot to write these squiggly braces. Okay. So, and I also forgot a new line, which is going to make this impossible to parse. Okay. So here I have code 10, and I start with node index 0. And I go to node index 1. 10, I start at node index 0, and I go to node index 1. So that seems like a bug. Because 1 we already used for 3, which was supposed to be a left path here. So maybe we can say stood debug print walkdir just to see what happens. Okay, so here, code. What's happening here? Code is 10. Oh, because it's value to code in here. Okay, so we have value 3, code 0. But then we have code 10 immediately right after. Oh, fuck, because we've incremented the code already. God damn it. This has to go way down here. Oh, that's fucking annoying. Okay, so here, code 0, 0. And we've made a mistake where our code, like our iterator over this code, needs to know how many bits it's expected to walk. That's important. So here we need to take in bit length. And the bit index is going to just be 64 minus bit length. Is that right? Maybe. So here, we're going to instantiate this thing with a bit length of 4. And here, we're going to instantiate with a lm length bit length. Okay. I don't know, man. We'll see. We'll just figure it out. This is supposed to be U64, I guess. Ah, fuck it. I don't know, man. I don't know. So many type issues. Int cast here. Okay. So let's zig build test. Make sure that our tests are passing still. True, true, false, true. False, true, false, true. So we just need to, like, let's not do this 64 minus. I don't think we need it anymore. Oh, maybe we do. Fuck. Okay. +1? Off by ones are hard, man. Okay, tests are passing. Zig, build, run. Okay. So here... Oh, it looks like we got through it okay. No invalid access of branches. So here we went, for code 0, we walked left. Then for code 10, we walked right, then left. Then for 110, we walked right, right, left. And then for 111, we walked right, right, right. So we should be fucking chilling. And so now, just to get really crazy at the end of this, we should be able to, once we have our new table, we should be able to print a new codebook. So codebook 2 is going to be table 2 generate codebook. And if the codebook comes out, it should be the same as what we tried to write in. Not quite right. No thing called generate codebook in this, because we need to try here, probably. Except that we need to store the root node. That was the last piece, so root is going to just be a usize, I guess. Here, root is going to be nodes items len -1. And here, root is going to be 0 because we put the root in first. And then when we get the root index, we just return self root. Okay. He doesn't like that, which is annoying. So he's hitting an unreachable. He's saying, hey, as I walk this thing, I should always get a branch. Side note, we could do... it's okay. We're not going to change this for now. Oi, 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 oi. Can we... Node from code. Generate codebook. Node from code. Path items. Path to bit representation. Blech. Blech. Why is this not working? Can we print the table, maybe? And maybe that'll... We are printing the table, so maybe that'll give us a clue. So we have an array list where we have our root item is a branch that goes left 1, right 2. So this is 0, left 1, right 2, a new branch. The second branch goes left 3, right 4. So left 3, right 4. Yep. 4 has a branch left 5, right 6, 5, 6. So I don't see anything wrong with this tree. This tree feels right. Like I don't see, like this is definitely, this is a valid tree. So then why is my codebook generation for this tree invalid? So we start with path.append 0. We try to take the left path. Why do you shift the code down by 64 minus bit index while you iterate? Shouldn't you shift down by code length -1 minus bit index? Because the code is a 64-bit thing was my thoughts. So I was trying to say how far into the 64-bit thing are we? And then it just kind of evolved that way. I think it's right. Pretty sure it's right. But I mean, I think there's probably a simplification that can be done here. Like the fact that we only ever use bit index with 64 minus bit index is like, there's something wrong there for sure. Or not wrong, but like suboptimal by a lot. Ugly. Confusing. However you want to call it. Okay, what the fuck is going on here? So we are saying, we're iterating by making some path. We try to walk that path, and as we try to walk that path, it gets mad. So can we say std debug print code is this code? And we'll format it as binary. And we'll new line here as well. And this will give us some clue. So here we're going right off the bat. Code is 0. Oh, and we take the left branch and we end up at a leaf node. Okay. Oh, that's interesting. So this codebook generation was assuming that I could walk left, but sometimes I can't walk left. So here, I just shouldn't assume that that's invalid. Right. So here, if it's a leaf, I just return. I think. Or break. Yeah. Oh yeah, okay. And so then I should end up with the code book here. Which is fucked. We only walked one guy. So here, let's see. It's because this walking code is invalid if the first thing that we hit is a leaf. So we just have to fix that. So it's we append a 0. If it's a leaf, we need to just turn it into a 1, the path. We need to go from 0 to 1. So why aren't we doing that? We say while path items.len is greater than 0, greater than or equal to 0, and path items equals 1, path pop. If path items len equals 0, break. No, okay, so if path items len is equal to 0, we break. Otherwise, we should reassign our thing to a 1 and try to walk right. So why the fuck doesn't that happen? GDB target. Zig out, bin, ziglib. Break on this line, run. Pre-path. Oops. Continue again. Are we in the right version? This is the U10 version, U10 version, U10 version. Fuck. U2 version. Okay. P-path. So he has a length of 1 with a 0 in him. And we find ourselves a leaf. Okay. P-path. Great. Keep going. Next. P-path. Length 1. P-path. Yeah, he's still good. P-path items 0. Pointer. He's a 0 still. But here we shouldn't be. So we hit next. Oh yeah, now he's a 1. Okay, so that's great. So now he should be walking the right branch. So that must not have been the bug. So we say node from code, switch node. It's a leaf again? That's probably where it's getting confused. P node. Yeah, he does think he's a leaf, even though he took the right branch, which he shouldn't have because our tree says that if we were to go right, we should go to element 2, which is 0, 1, 2, which is a branch. So that's the bug. Is that he tried to go this node from code. What the fuck? So for code value, he looked at the item at that index. Oh, this is not starting from the root. God damn it. God damn it. Which means that this could go back to unreachable probably without any bugs. There we go. So the code book we generated from our thing said 0 is 3, numbits 3, 1 is numbits 3, 2 is numbits 2, and 3 is numbits 1. And does that match up at the very least with what we punched in? 3, 3, 2, 1. 3, 3, 2, 1. Oh my god, what a pain in my ass. But I think we finally got there. I think we got to the point where these canonical Huffman codes can now be used to generate our tree, which we can use to walk our encoded data. And we can... I guess that's it. That's kind of what we did. And I guess we also did Huffman... Our Huffman thing is now like allowed to use variable types. So we should be able to use it for this like 285 value thing instead of 256 value thing. Ugh. What a pain. We finally got there, though, so thanks for watching, guys. I think we're going to call it there. If you liked what you saw, we stream most days at around 2 o'clock Pacific time for 2 hours. So right now it's close to 4 Pacific time, so anywhere between 2 hours ago and now. We're working right now on this like zlib re-implementation in Zig, which already exists, by the way, in the Zig standard library. We're just doing it for fun. And yeah, we'll probably be going on this for a couple more days at least. There's a bunch of other projects that we've kind of done in the past that are all on the YouTube channel and the GitHub, so there's links to those in the Twitch description. But if you can't see them, then it's the same username on both. Let's see. So what have we worked on before? Like operating systems, neural network, virtual file systems, some web dev stuff, kind of like a variety. The like trend is lower level things I feel like doing that day. Git GUI, diff algorithm, stuff like that. So I think that's it. Thanks for watching, guys, and I'll catch you on the next one. Bye.